everybody. We are going to continue on with our gas laws. I think just to save time and also seeing today that it took you about like 5 seconds to do the Boyle's Law worksheet, I'm just going to go over what each of the gas laws are, and then I'm also going to go over the formulas for each gas law, but I'm not going to really do any example problems because it's really as simple as figuring out what numbers you have, plugging them in, and solving for your answer. So I'll go through Charles' law. We have another law called the Gay-Lussac's law, and then we also have the combined gas law, and that will correspond, I think, a lot with Boyle's law. And then we have one more that I was going to do, but I think that I'm going to save the ideal gas law for when you come back on Monday. So hopefully the video shouldn't take too long. We'll start off with Charles. Remember, the first one we did was Boyle's, and Boyle's gas law was comparing, or we were working together. Let's go back to that slide, actually. Remember that Boyle's gas law is showing you that pressure and volume are inversely related with one another. So if I decrease the volume, then what's going to happen to pressure? So if volume is decreasing, remember then that pressure would increase, because if something is inversely related or indirectly related, it simply just means that the opposite things are happening to one another. So if volume is decreasing, then pressure would be increasing. If volume is increasing, then pressure is decreasing. And Boyle's law, again, remember, was P1 V1 equals P2 V2. So Charles's law is really relating volume and temperature. So like Boyle was relating pressure with volume, Charles's law was dealing with volume and temperature. So Charles's law states that as temperature increases, so does the volume of gas when the amount of gas and the pressure do not change. So in Charles's law, if temperature increases, volume will also increase. So this would be a direct relationship. So these two things are directly related. What happens to one variable will happen to the other variable. So I can see in this picture here, I have a sample that has a temperature of 150 Kelvin, and then it's at 1 atmosphere. Well, let's say that I heat up this sample, that it now has a temperature of 300 Kelvin. If I look now, my pressure is going to be much greater. And so then my volume will also be much greater. So I started off with 150 Kelvin at 300 milliliters. I heated up this sample to 300 Kelvin, and now I'm at 600 milliliters. So my temperature increased, my volume also increased. So Charles is dealing with volume and temperature. And remember, they are directly related, just meaning that what happens to one happens to the other. So one of the things that was in that figure was that we also said that the temperature was in Kelvin. And that's really important that you know that Charles's law will deal with the Kelvin scale. So absolute zero, we know, is just 0 on the Kelvin scale. And Charles's law states that the volume of a given amount of gas is directly proportional to its Kelvin temperature when that pressure is held constant. So I have V1 over T1 is equal to V2 over T2. So this is Charles's law. And we have to use Kelvin for the temperature. If it's in Fahrenheit, if it's in Celsius, you're going to have to convert. And if let's say that I give you the temperatures in Celsius, and then you'll have to convert to Kelvin, and I may ask you for your answer in Celsius, which means that you would have to convert back. So usually we'll just use the Celsius to Kelvin conversion. So we know that if I'm going from Celsius to Kelvin, what would I do there? Remember, we would add 273. And then if we were going from Kelvin to Celsius is when we would subtract 273, just as a little refresher. So Boyle's law is P1 V1 equals P2 V2, and it's stating that pressure and volume are inversely related or inversely proportional to one another. Charles's law is saying that volume and temperature are directly proportional, and Charles's law is a V1 over T1 is equal to V2 over T2. So I have an initial volume and an initial temperature. It's going to be equal to the proportion of the final volume over the final temperature. Remember, directly related. What happens to one happens to the other. The third gas law, so we did Boyle's, the last one we did was Charles's gas law. This one is called the Gay-Lussac's gas law, and this one is going to relate pressure with temperature. So Gay-Lussac's law states that pressure with a fixed amount of gas will vary directly with the Kelvin temperature as long as volume will stay constant. So pressure and temperature are going to be directly related, meaning that we're going to have, if pressure is going to be increasing, then temperature will also be increasing. So what happens to one happens to the other. And if we look at this figure, I'll see that I have my temperature at 150 Kelvin at 1 atmosphere. Now I'm going to heat up my sample to 300 Kelvin, and I see that now my pressure increased to 2 atmospheres. And in this case, my volume stayed constant. I have 1 liter, so nothing happened to the volume. So the only thing in Gay-Lussac's law is pressure and temperature. And again, what happens to one happens to the other, so they're directly related. So Boyle's law, P1V1 equals P2V2. Charles's law is V1 over T1 is equal to V2 over T2. And then Gay-Lussac's law is P1 over T1 equals P2 over T2. So Boyle's is pressure and volume, Charles is volume and temperature, and Gay-Lussac's is pressure and temperature. Okay? Lastly, of what we're going to talk about today with gas laws is the combined gas law. And the combined gas law just takes Boyle's, Charles, and Gay-Lussac's and combines them all together. So it's going to show a relationship amongst pressure, temperature, and volume for a fixed amount of gas. So I have a certain amount of gas, and then I'm going to look at the relationship between pressure, temperature, and volume of that gas. So if we take all of the 3 gas laws we did before, Boyle's, Charles, and Gay-Lussac's, then I can get this as my combined gas law. P1V1 over T1 is equal to P2V2 over T2. I can pick out Boyle's law right now. P1V1 equals P2V2. I can pick out Charles' law right now. V1 over T1 is equal to V2 over T2. I can now pick out Gay-Lussac's law. P1 over T1 is equal to P2 over T2. So all we did was combine all 3 together. And just in case, I really liked this table because I thought they did a really good job of maybe organizing this for us, that Boyle's law has that formula, Charles, Gay-Lussac's combined, and then they're showing you the relationship here. So pressure, volume, and temperature are these really big things in terms of gas. So Boyle's law is really looking at the relationship between pressure and volume. Charles is looking at the relationship between volume and temperature. Gay-Lussac's is looking at the relationship between pressure and temperature, and then the combined one looks at the relationship amongst all 3 of those variables. And then we can see here also what's going to be kept constant in each law. Okay, just a few more slides and then we'll stop because I just want us to get up to the point where we get to the ideal gas law. So Avogadro, we have seen him before in terms of mole and Avogadro's number. So Avogadro also has a principle that states that equal volumes of gases at the same temperature and the same pressure will contain an equal number of particles. So if I have different samples of gas and they're all at the same temperature and they have equal volumes and they're all at the same pressure, then they're going to have the same amount of particles in each sample. So I can see here I have 1, 2, 3, 4, 5 particles of carbon dioxide. We know those would be molecules. And then I have helium. 1, 2, 3, 4, 5 particles of helium. And then I have my oxygen. 1, 2, 3, 4, 5 particles of oxygen. So we're assuming that these are equal volumes same temperature, same pressure, and as long as those three things are the same, then these should contain an equal number of particles, and that's just Avogadro's principle. Next I have the molar volume of a gas is the volume that 1 mole occupies at 0 degrees Celsius and 1 atmosphere of pressure. 0 degrees Celsius and 1 atmosphere also have another name, and that is that we call those standard temperature and pressure, or we'll abbreviate it STP. So I could say that, change this instead to say the molar volume of a gas is the volume that 1 mole will occupy at STP, because it's when I have 0 degrees Celsius and 1 atmosphere of pressure. So molar volume is just really thinking about the volume in terms of how many 1 mole, or how much 1 mole will occupy at STP, which is 0 degrees Celsius, 1 atmosphere. Another kind of conversion factor that we'll also work on is that at STP, at standard temperature and pressure, 1 mole of gas will occupy 22.4 liters. So this is very similar to the whole 1 mole of anything, 1 mole of particles is equal to 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules or formula units, any of those things. So at STP, 1 mole of gas is equal to or occupies 22.4 liters, just like 1 mole will equal 6.02 times 10 to the 23rd particles. Okay, for the ideal gas law, this is where we're going to stop, and we'll come back to this slide on Monday. So for all you need is remember Boyle's law, and remember those pressure conversions, because you'll need to know those for Monday. Charles' law, combined gas law, Gay-Lussac's law, and then Avogadro's principle. Those are the things that I'm going to ask you about on Monday, and then we'll start off on Monday with the ideal gas law. Okay, I'm going to post also just a few practice problems over all of the gas laws that we've gone over today. So if you want to try to do those on your own, you're more than welcome to do that. Maybe that will help some people, but you by no means have to do them. And I will see you on Monday. I hope you guys have a great weekend. Bye!